Hello and welcome back to AP Pre-Calculus. Today's lesson 2.11 is on logarithmic functions. All right, guys, let's talk about some key characteristics of log functions here. So here's our function. This is a basic logarithmic function. There's a lot more stuff that could be going on, but let's just start with a nice basic one. So we got f of x equals a, which is our constant multiplier, the coefficient, log base b of x. And this b has got to be greater than 0. It cannot be negative and it cannot be 1. So it's got to be a positive number, but it can't be 1. And then we got our x value. What's another name for x? Well, input we've used before, but we've also used the word domain. And now that we're in the high level math classes, we talk about domain and range a lot more than we did previously in our algebra classes, okay? So on a basic logarithmic equation, our domain is going to be from 0 to infinity, and we didn't include 0. So x cannot be 0. If you took out your calculator and just did a common log and did log of 0, you're going to get an error, okay? Because any other number we can use. That's not true. Any other positive number we can use. So x has got to be positive, greater than 0. Well, what happens when it's not an x? What if it looked like this? Log x plus 4. Well, the number after log cannot be 0. It's got to be positive. So we take this x plus 4, set it greater than to 0, and just solve. So now I know that x has got to be bigger than negative 4. So my domain would be negative 4 to infinity. Okay? That's how we find our domain. Range for logarithmic functions is easy. It's always negative infinity to positive infinity. We used to be able to say all real numbers, but we got to get a little bit better at our communication. We are in a college level class, so we're going to write it in interval notation as negative infinity to positive infinity. Let's look at our first graph here on the left. This is when our a is positive, so that multiplier on the outside is a positive number, and our b is bigger than 1. Remember, our b has to be positive, but it can't be 1. So if we're talking about numbers bigger than 1, it looks like this graph. It starts out moving up really fast, and then it starts leveling out, but it's never going to level out. It will always increase, right? It'll just increase slowly, all right? So this is when our a is positive and our b is bigger than 1. Let's look at this guy over here. This is an a is negative. Really, this should remind you that, oh yeah, negative out in front flips us over the x-axis, right? So instead of increasing, we decrease. All right, let's look at this box. So logarithmic functions, just like exponential functions, are always increasing or always decreasing. They'll never switch from one to the other, which means we'll have no relative maxes or mins. We call that extrema, right? Unless it's a closed interval. Like if I said, hey, I'm going to go from here to here, I'm not going to the infinities, we might have one, and we would, okay? But if we're just talking about the function as a whole, we would never have a relative max or a min, all right? And if I'm increasing or decreasing, that also gives us the idea of concavity, okay? A lot of times we'll be able to look at this and say, oh, that's concave down. Looks like I'm starting to go down, and if I kept going in this direction, I'd have a concave down. Over here, if I kept doing what it starts out doing and finishes the curve, that would be concave up. Well, easily to see the concave up because it's still concave up, okay? So if we don't change concavity, if we don't go from concave up to concave down or concave down to concave up, we have none of those other points, the points of inflection. Remember, extrema is where we go from going up to going down, increasing to decreasing, or decreasing to increasing. Points of inflection is where we change concavity. Also where we change our rates of change, the slopes. If the slope goes from increasing to decreasing, that means we have a point of inflection, okay? Let's look at our end behavior here. So if we have a logarithmic function in general form, as the input x values increase without bounds, the output values will either increase or decrease depending on our a, okay? Since a logarithmic function have restricted domain, they are vertically there's a vertical asymptote at x equals 0. So as a result, the left end behavior would occur as x approached 0 from the right. Okay, so our limit statements, so as x approaches 0 from the right, we're going to either be going up to positive infinity or negative infinity. Let's look at our graphs. So here I am coming from the right, it's approaching negative infinity. On this one, as I come from the right, it's approaching positive infinity. What's happening as I go out to the positive infinity on x? Well, as I'm going out to positive infinity, my y values will either be going up to infinity or down to negative infinity, okay? Notice we didn't cross over into the negative because our input values cannot be negative in the general form. Like if we have some transformations, we might be able to have some stuff going on, but generally we can't dip into the negative domain numbers. So let's practice those limit statements, okay? So we are approaching 0 from the right on this first function f. So I'm approaching, what is my y value? It's going down to negative infinity. So I'm going to negative infinity. What about the right one? So let's write it out. Limit of f of x as x approaches positive infinity. What is it doing? So as I'm going this way on my graph, the y value keeps going up and up and up, so it is going to positive infinity. Let's try b. All right, what's going on here? So from the left, I want to go limit as x approaches 0 from the right. H of x is doing what? All right, let's look. So as I'm going this way, closer to 0, my y starts flying up to positive infinity. And then from the other one, limit h of x as x approaches positive infinity. What's going on? So as I'm going this way, my graph keeps getting lower and lower and lower, which is negative infinity. So doing that in graph form, not that hard. C is in equation form. I'm going to be honest, I would probably just go ahead and graph it. Since our A is positive, it's going to look like this. Okay, so I get the same idea as A here. So I would have limit of g of x as x approaches 0 from the right. We are going down, so negative infinity, and then limit of g of x as x approaches positive infinity. I'm going up to positive infinity. And that's how you do those. All right, using some different vocab words here, concave up, concave down, increasing, decreasing. So let's look at the graph. It's pretty simple. Like if I were to have you draw this and you think you should do something like that, that would be concave up. So I would choose concave up. But the height of the graph starts out really high and gets smaller and smaller and smaller. So it is decreasing. All right. For B, like you feel like if you trace in the graph, you feel like you should keep it and go down like this because we're used to doing quadratics. So it would look something, and that's concave down. So this one would be concave down. But as I start at 0, I'm really low, and as I move to the right, I start getting higher and higher and higher. So my y values, the height, is increasing. What about the next one? I would graph it again. Because our A is negative, it flips over the x-axis. So what's going on here? Well, it's the same as the first one, right? So it is concave up and decreasing. All right, so here we have several logarithmic functions. We got some tables, and we got a missing value in there. We got a k in each one of those x's. And remember, for a logarithmic function, the x's have to keep getting multiplied where the y's keep adding the same thing over and over again. So if you look at your y's, 1, 2, 3, 4, 5, the y's are looking good. Let's look at our x's. Well, I'm multiplying by 2, which means I got to multiply by 2, which means I multiply by 2, and multiply by 2. So what would the k have to be? Well, I'm at 2 times 2. K has to be 4. Let's look at our y's for the next one. 0, 5, 10, 15, 20. That looks good. I don't know what we're multiplying by, but to get here, we're multiplying by 3. To get there, times 3. To get there, times 3, which means we had to multiply by 3. So you could look at it this way. 3 times what gives us 6? Or start from 6 and go backwards and divide by 3. And you would get k equals 2. All right? H is good. So let's look at here. Uh-oh. What did I multiply by? So now I have an issue here, right? Because I'm not multiplying by the same thing, but they told me it definitely was a logarithmic function. So let's find the differences here. From 4 to 5 is 1. From 5 to 7 is 2. And so if my differences are being multiplied, that's another way to show that it's a logarithmic function if on the x's. So what would I have to multiply by for the next one? I would had to be 4. So that means that between 7 and k, there has to be 4 different, right? What's 4 different from that? Well, that's going to be 11. Let's just check. From 11 to 19, is it 8? It is. So we're doing pretty good there. Let's look at this one. Again, we're not really multiplying. Well, are we? We could be multiplying by e to the third. Let's see. This one is multiplying by e to the third. So this one has to be multiplying by e to the third. Well, what's e times e to the third? That's e to the fourth. Let's just check real quick. If I do e to the third here from e to the fourth, do I get e to the seventh? I do. There we go. All right, last example. They want us to find the domain and range of these log functions. Guys, we can do the range real quick on all of these because they don't change. Every single one of them is going to be from negative infinity to positive infinity. Nothing can change my range, okay? So I'll put those in there first. But my domain is all about that guy and that guy and that guy. So that definitely is going to give us some issues, okay? So we can't have 0. I'm going to take the thing that's after the word log and I'm going to set it greater than 0 because it has to be bigger than 0. Well, I don't have to do anything. So all the numbers from 0 to infinity are good for my domain. 0 to infinity. That's a terrible infinity, but it's going to work. The next one, a little bit of an issue. I have x minus 3 is greater than 0. Well, that's not hard to fix. So we get from 3 to infinity. That's a little bit better, infinity. So what is that doing to our graph, right? So this one, we should be used to this one by now. It's going to look something along the lines of this, right? And we have a vertical asymptote at x equals 0 because we cannot touch that line. So if I wanted to put vertical asymptote right there. All right, let's move on to the next one. So do a little graph here. So this time, because my a is negative, I'm going to flip, right? But I've also shifted 3 to the right. So now my vertical asymptote is over here. I have a vertical asymptote at x equals 3. But my graph actually shifted, okay? So this time it's going to go like this. And then the last one, I'm going to take my 2x plus 3, set it greater than 0, do some solving. I get negative 3 halves, and I get negative 3 halves to infinity. And then I would have a vertical asymptote at x equals negative 3 halves. All right, that ends today's lesson.